Maar gewoon totaal maar overgebogen.
So before the break we were discussing, we started to discuss what kind of surfaces you have to modify. Yeah. Importantly, we discussed the two main strategies you can use if you want to change your surface properties. So either you adsorb molecules on your surfaces and you just have physical interactions, or you can do some chemical reactions and you have covalent anchoring of molecules on your surfaces. Yeah? And if you do covalent interaction, then you have something which is more stable than if you just have physical interactions. Yeah? And then after we reviewed some standard, let's say, approaches, so if you want to modify glass and silicon surfaces, those are covered with silanol groups. So you can use a reaction which is called synanization, yeah? And then depending on the molecules you can add on your surface, then you can create hydrophobic surfaces, but you can also create reactive surfaces. And that's something we will discuss afterwards. And then in terms of gold, what you would do is a chemisorption or creation of self-assembled monolayers, SAM, and for that you work with thiolated molecules. Yeah? And then before the break, we were discussing how you can implement these strategies to create surfaces which are more hydrophilic or more hydrophobic. Yeah? So why do you want to do that? Why do you want to have surfaces which are more hydrophilic or more hydrophobic? So one example that you were mentioning, yeah, she's not looking at me, is depending on the solution you want to introduce in your channel, you would like to have hydrophobic surfaces or hydrophilic surfaces. Yeah? So something that you can do in microfluidic devices is to have something which is called a two-phase flows. Yeah? So what you will do is that you will create smaller compartments of a certain liquid in your microfluidic channel. Yeah? So if you want to create some small reactors, some small droplets based on water, yeah? What you do is that you use an oil phase or an organic solvent, that would be your continuous phase, and then you will create these aqueous droplets of water. Yeah? So at the end, you still work with an aqueous solution because you care about what's happening in your droplets. Yeah? But then the liquid that will see the walls of your devices, yeah, is the oil phase. So then if you want to have something which is stable, then you will do some hydrophobic treatment of your walls. Yeah? And then typically if you work with glass, you will do a synanization and then you will work with, for instance, some silan with a C18 in terms of, so alkyl chain with 18 carbon groups. Yeah? Yeah? But you can also do the contrary, so you can also say, okay, I care about having droplets based on oil, yeah? And then your continuous phase will be water or aqueous phase. And then in that case, you're really happy to have channels which are highly hydrophilic. So you may still want to do some hydrophilic synanization. Yeah? So you will add a silan. And if you want to have a silan which is hydrophilic, typically you will work with something with an amino group. Yeah? So that's one application. Yeah? Another application is to make valves. Yeah? So your liquid, if you have a channel which is hydrophilic, your liquid will go will fill in your channel very quickly. If your channel is hydrophobic, then your liquid will go slowly, yeah? And then you may have to apply a higher pressure if you want your liquid to go in your channel. Yeah? So what you can do, for instance, is that if you have a channel based on silicone or glass, so material is hydrophilic, and at some point you want to stop your liquid, yeah, at a given location, then what you can do is that you can create somewhere a hydrophobic patch, yeah? And since your surface is hydrophobic, then the liquid will not progress, yeah? And then if you want your liquid to progress, then you need to apply a higher pressure. Yeah? So in that case, so this is a completely different approach that we have not discussed, but you can have a gas phase deposition of a CF3, and then you can, if you do that in a localized way in your channel, then you know that locally you will create a hydrophobic patch, and that would be a passive valve in the sense that there is no active process to stop the liquid, like some active valve would be something that you would close physically, for instance, but here it's more that passively the liquid will stop when the liquid meets this hydrophobic patch. Yeah? And then this is, again, you can quantify that with a contact angle. So for instance, if you have a silicone channel, your contact angle will be 4 degrees, and then if you have this patch with CH3, then you will have a contact angle which is much higher, so 100 degrees. So you will have something which is highly hydrophobic. Yeah? And another application, so if you want to spot molecules on a hydrophilic surface, yeah? So if I have a hydrophilic surface and I add a droplet of molecules in aqueous solution, yeah? What happens is that my droplet will spread and spread over the surface, yeah? But if I want to confine my molecules on a small surface area, what I want to do is that I want to keep, let's say, my droplet on a confined area, yeah? So, for instance, if you think of applications like biochips, so where you want to spot molecules on the surface, yeah, and you want to analyze your molecules, if you have a low concentration of molecule in your droplet and your droplet is spreading over the surface, then the concentration of molecules at the end of your surface will be very low because you have a lot of spreading, yeah? If you manage to confine your droplet and you let the droplet evaporate, yeah, then all the molecules will just be confined, let's say, on the surface area, on the interaction between the surface of interaction between your droplet and your surface. So on the surface at the end, you will have a higher concentration of molecule because it will be on a smaller spot. Yeah? Is that clear or not? Yeah. So what you can do, for instance, is that, so what I was saying, so if you have smaller spot, then you will have a higher concentration of molecules on the surface. Yeah. And if you want to analyze these molecules, yeah, with different types of techniques, then you know that you will increase your sensitivity of detections because you will create locally a higher concentration of molecules. Yeah. So what would you do to prevent spreading of your water on the surface?
Make it hydrophobic.
Yeah, you could make it hydrophobic, yeah. But if you still want your droplet of water to anchor somewhere on the surface, if you really want to be sure, for instance, if you have a surface which is only hydrophobic, your droplet may move, you know, so you cannot really localize.
Just make a really small piece hydrophilic.
Yeah, very good. Yeah, and the rest is
Hydrophobic.
yeah, that's what you can do. So if you want to spot molecules on a large surface, but you want to confine your molecules at given locations, you can create a balance, like for the valve, or hydrophilic surface and hydrophobic surface. Yeah? And that's yeah, one example. So here, so it's for a certain technique of analysis called MAT-DMS, and I will introduce that later in the course about biomolecular interactions. Yeah? But if you want to analyze your molecules with MAT-DMS, you need to deposit your sample in the shape of droplet on the surface at given position. Yeah? So what they did here is that they have a hydrophobic surface. Yeah? So for instance, here they can use chemicals with alkyl chain between 4 or 18 carbon, so you will create a hydrophobic matrix. Your whole surface will be hydrophobic. But then everywhere you want to deposit your molecules for the analysis, you will create hydrophilic spots. Yeah? So you will use the same strategy because you will have the same material. Yeah? But here you will use molecules, for instance, with the alcohol group here, because you know that alcohol will give you a hydrophilic surface. Yeah? So if you want to spot molecules, for instance, on the surface, and you want to know where your molecules would end up, then you can have a balance between hydrophobic surface with hydrophilic spots. Yeah? Is that clear? So we move on with the examples and applications, and now we are going to discuss how can I immobilize biomolecules in a covalent way on my surfaces. Yeah? So how would you do that? Do you have an idea? More in general in strategy, not really in terms of precise chemicals, but how would you do that? Yes?
It uses like antibodies, right? The sort of molecules have a high affinity for a certain analyte, so you can bond them to a surface and then the analyte will get stuck there.
Yeah. But you stick to my question. How do you immobilize your antibody on the surface? Because your antibody is also a biomolecule.
Yeah,
So you start with a substrate without anything and you want to immobilize a biomolecular antibody. How do you do that?
for example, with a gold surface, you can add the SH group to your biomolecule, the antibody, add that one in, and then have the reaction like that.
Okay.
Yeah, chemistry is nothing but
Good.
some
Yeah,
sort of
no.
reaction with the...
Yeah, the idea sounds good, yeah. Yeah. Okay. Any other idea? So his suggestion is I have a substrate, I have a molecule that I want to attach on my surface. Yeah? So he suggests I change my biomolecule so that this biomolecule has a group that can interact with my substrate. Can you think of another strategy? Change the surface, yeah. That would be the first step you would do. But the other one is also good if you can modify the chemistry of your biomolecule. Yeah. So the generic strategy is that you would start with the surface, yeah, and then you will change your surface, your chemical properties of your surface, to introduce a reactive group, yeah, and then this reactive group, you know that it can interact with the biomolecule you want to attach on the surface, yeah. And another strategy I had not thought about is that you first change your biomolecule and then you add it on the surface, yeah. That's another one, but most of the time people start on the surface. They change the chemical properties of the surface to have something which is reactive that can react with the biomolecule you want to attach on the surface. Yeah? So that's a general strategy. So what kind of groups, what kind of reactive groups you can use if you want to immobilize a biomolecule? So there are not so many groups you can think of. Yeah? So a group I already mentioned is a amino group, yeah? NH2. Yeah? Another one is a carboxy group, so COH, aldehyde also, COH, and epoxy. So this is the epoxy where you have a ring structure with an oxygen atom and 2CH2. Yeah? And why do you want to use these molecules? Yeah? Because amino groups can easily react with carboxy groups, aldehyde groups, or epoxy groups. Yeah? And what is nice is that you can do the chemistry in water. So if you think about biomolecules, you prefer to keep them under aqueous solutions. Yeah? So you're happy to work with these groups because you can do the coupling in aqueous phase, and it's not always straightforward, but it's possible to have interactions between these, to have chemical reactions between these different groups. Yeah? So the coupling chemistry is well established. As I said, it can take place in aqueous phase. And for instance, in terms of biomolecules, if you think of proteins, proteins are covered with amino groups. Yeah? So if you can take advantage of the amino groups, and you know that if on your surface you will have either carboxy groups, aldehyde, or epoxy, then you can easily immobilize your protein on the surface. Yeah? Is that clear? Yeah? So, so that's important that you remember the strategy, yeah? And now I will show you how it works, but I don't ask you again to remember all the names of the different chemicals, yeah? Just to give you an idea about how you do it, yeah? So if you want, for instance, to immobilize a molecule with an amino group, yeah, and then your surface is terminated with a carboxy group, COH, yeah. So COH, carboxy group, they are not very reactive. So the first thing you need to do is that you need to activate your carboxy group so that it's more reactive, and then it can interact with the amino groups, yeah. So what you do is that you do activation with two chemicals which are called EDC and LHS, so ethyl carbodiimide, and then hydroxysulfoxyimide, yeah? So this is how it looks like. Please don't remember that. But what you have to keep in mind is that you can have interaction between a carboxy group and an amino group, and then you can create a covalent bond, yeah? And then you can immobilize a biomolecule with an amino group on the surface, yeah? If you have an epoxy terminated surface and an amino moiety, so amino group on your biomolecule, then again, there is no activation, and you can also create a covalent bond between your epoxy group and your amino group. Yeah? And the last one is aldehyde groups. So this is an aldehyde group. And again, you have a molecule with an amino group, and then you can easily create a covalent group between your two molecules. Yeah? So these are the three strategies. So if you want to do covalent immobilization of biomolecules with an amino group, like a protein on a surface. Yeah? But there is another approach, which is maybe sometimes easier to implement. Yeah? So instead of having something which is completely covalent, you can use an approach which is almost covalent. So this is something which is widely used in biology. Yeah? So instead of having directly immobilization of your molecule, so here this is the yellow part on the surface. Yeah? You can also use something which is called an avidin-biotin interaction. Yeah? So what you do is that this avidin and biotin, yeah, I will explain it after, or you can use IgG protein A interactions. So you have a substrate, yeah? So actually, this is a bit what you were suggesting. So you have a molecule you want to attach on the surface, and then on the molecule you will couple another group. On the surface you couple another group, and these two groups, they can interact and they can have a very strong interactions, yeah, which is almost covalent, yeah. So these two molecules you can use are avidin and biotin, so this is a couple, and that gives rise to very strong interactions. Or you can also use the couple IgG and protein A, yeah. And yeah, a bit more information about avidin biotin. So biotin is a vitamin, avidin is a biotin binding protein, and it's a tetramer. So you have a very, very strong interaction. So it's not completely covalent, but it's almost covalent, yeah. And what is nice is that the reaction is instantaneous, so it's really, really fast, yeah. And it's really strong, and it resists a lot of harsh conditions, yeah. And one issue is that the avidin is a tetramer, yeah, mean that it can interact with 4 different biotins. So you may want to block the other groups if you don't want to have like a formation of large structures, yeah. So this is more like a complement of information, yeah, for you. That you can also use other strategies which are not always based on this chemistry with amino groups and carboxy or aldehyde and epoxy groups. Yeah? Is that clear? Yeah? So a last point about protein immobilization. Yeah? So sometimes you don't immobilize directly your protein on the surface. Yeah? Why? Because your protein is a 3D structure. Yeah? And it's completely covered with amino group. Yeah? And if you just immobilize your protein on the surface, you cannot really control the orientation of your protein on the surface. Yeah? So this is what I represented here with my beautiful cartoons. Yeah? I have a substrate. Here I will have my reactive group that I can use to immobilize my proteins. Yeah? And since my proteins is covered with these amino groups, my protein can sit on the surface with different configurations. Yeah? But if I want to control, or if I want to have access, for instance, to this pocket, let's say, for any application, I'm interested in this pocket. So here I have access to this pocket, here I have access to this pocket, but here I don't have access to this pocket because it's directly interacting with the surface. Yeah? So what you do is that you can use a spacer. Yeah? So what you do is that here you have a reactive group, and instead of having a direct reaction between your reactive group and the proteins, yeah, you will have an intermediary spacer here. So something long and thin, let's say, a bit flexible, yeah, that will have 2 reactive groups to react with the surface here and to react with your proteins. And then you bring your proteins further away from the surface so it can move, and then you're sure that you can always have access to any site of your protein. Yeah? This is also a complement of information. Yeah? So how can you do that? Yeah? So I go back to surface like glass and silicone. So I have my silanol group here, and then I start to immobilize aptes. So aptes is nice because I have a silan group here, and I have an amino group here. Yeah. So I end up with a surface which is amino terminated. So I know that I can use the amino groups to immobilize other molecules. Yeah. And I know that my amino groups can react with carboxy groups, epoxy groups, or aldehyde groups. Yeah. And then there was this molecule called glutaraldehyde, which has 2 aldehyde groups here. So one will react with my surface, yeah. And then I have another aldehyde group here, which is available, and that can react with another amino group, yeah. So with that, I can have a protein which is further away from the surface, yeah. Is that clear? Yeah. Are you starting to all fall asleep or not? Yeah.
No, not yet. But you have the 2 the same groups on the on opposite sides of the I'm not sure what it's called, the aldehyde groups, I think so.
This one you mean?
Yeah.
Yeah.
How do you make sure that it does not react also with the one next to it? So you have the blocking of the active sites. Do you have no more active sites left?
The spacers don't stick to each other.
Yeah, I'm not very sure how you do that actually. What I was discussing actually with your colleague, I think that if you have 2 reactive groups, if one has reacted, maybe you decrease the reactivity of the other group. So you will have preferential interaction with something with 2 active groups than with 1 active group. That's what I would think of, yeah. But I have no, how to say it, practical experience with
maybe
this.
it's not
Yeah,
even possible.
yeah,
but-
yeah. It's it would be. I think it would be possible, yeah. But in terms of glutaraldehyde, so you have a chain which is short, but if you work with things which are maybe longer, then you have a preferential orientation perpendicular to the surface. Yeah. Yeah. But it's a good question, but I don't have any answer. Sorry. Yeah. So that was about the the chemistry. Yeah. And then in terms of patterning approaches, what I was saying earlier that maybe you want to create spots of your biomolecules on the surfaces, yeah? So what I was saying earlier is that maybe you can first create a surface with hydrophobic hydrophobic properties and then some spots or hydrophilic properties, which takes a lot of time because after you need to do some more surface chemistry on your hydrophilic spots, yeah? But you can also maybe use physical surfaces, physical approaches to pattern biomolecules on the surface. Yeah. So this is reviewing some approaches you can use. Yeah. So for instance, you can create a stamp. Yeah. So most of the time, PDMS is used as a stamp, and then you can incubate your stamp with what is called an ink. So it's just like your solution with your biomolecules. Yeah. So the surface of your PDMS will be covered with these biomolecules, so they form a layer and they can also penetrate maybe a bit in your PDMS. Yeah? And what you do is that you bring this stamp after in contact with the flat surface, yeah? And only the spots which are touching, let's say, the surface can deliver the molecules on the surface. Yeah? So you could have physical interaction, but you can also have something that you have prepared your surface to activate your surface, and then you can have chemical interactions between your ink, so the molecules in your ink and your surface. Yeah? And with that, you can pattern your molecules on the surface. So that's one approach, which is nice because you can easily create large surface areas if you have a stamp which is large enough. Yeah? This is another approach which is also covering a large surface area, but another approach is that you can also print your protein on the surface. So how does that work? You have a tip, a cantilever here, which is hollow, so you have liquid in your cantilever or you have liquid around your cantilever, and then you come with your tip close to the surface, and every time you almost touch the surface or come very close to the surface, then you can deposit your ink on the surface. Yeah. And then if you can scan your surface and regularly, let's say, approach your surface, then you can also create patterns with the molecules you want to deposit on your surface. Yeah? And so in our group, so again, the fluorescence picture is not coming, yeah? So we have such a device to pattern molecules on surfaces, yeah? So it's a nano enabler. So here you have the tip here. You can deposit the solution on the tip, and the tip looks like that. So you have a reservoir, and then you have a channel which is open, and this is your cantilever here, where your liquid will come, and then every time you approach the end of your cantilever to the surface, if you do that in a controlled way, then you can just deposit a small amount of your liquid on the surface and your molecules. Yeah? And then depending on how you do that, how close and how much force you apply, then you can also control the spot, yeah, the side of the spot. And this is what you see here on the picture. Yeah. Do you have any question about that part, about immobilization of molecules? Everything is clear? Okay. So the last part is about flow control. So so it's about flow control and separation. So now we've been discussing about hydrophilic, hydrophobic. How can I create some reactive spots to immobilize specific biomolecules, and after you can also use that to immobilize cells. But the last series of examples is about flow control and separation. Yeah. So I will discuss that in more details after. So why do you need to coat your surfaces? Here is to stability and control your electroosmotic flow. So it's only when you have a electro-driven flow, so using an electric field, not if you just push if you just apply pressure, the surface properties have a different role, but here we will discuss about electro-driven flow, yeah? And another application is so capillary electrophoresis-based separation, so also using an electric field, yeah. And then another role of the coating is to decrease the absorption of the analytes on your surface, so the interactions, yeah. And that's what I was discussing at the beginning, that if you have a lot of interactions between your biomolecules and the surface, yeah, then you can have some bond broadening during your separation, yeah. So I hope you can understand that part, because usually you first have the theoretical part about electroosmotic flow and separation before I give this lecture, yeah. So something which is widely used in microfluidics to actuate liquid is what is called electroosmotic flow, or EOF, yeah. And what you do is that you don't really apply your pressure like you would do with a syringe pump or a column of liquid, but you apply an electric field, yeah. And the pumping is based on the surface effects, yeah. So how does that work? So I have a surface here, so for instance glass and silicone, so I have my cylinder groups, yeah, and they are negatively charged. So if my proton is gone, then I'm left with a SiO minus group, yeah. So I have a surface here which is negatively charged, yeah. If I have a charged liquid, so in my liquid I will have a lot of ions, yeah. So what happens is that all the ions which are positively charged, they are attracted by the surface, yeah. And that will form here what is called the Stern layer. Stern layer, so it's just a lot of cations that are coming on the surface and that will counterbalance the fact that you have charges created by the cylindrical groups on your surface. And then you have something which is neutral, yeah. And then close to that, you will also have accumulation of ions which are positively and negatively charged, yeah. And this is what is called the diffuse layer, yeah. So here you have creation not only on the surface, but you also have an interface here with different properties than the bulk, yeah. Because you will have close to the surface a higher concentration of ions compared to the bulk, yeah. So what do you do then is that you will apply an electric field. You apply an electric field at the two extremities of your channel, yeah? And then what happens is that, for instance, the positive ions, they will move to the negatively charged electrode, yeah? And then if these ions are moving, yeah, the cations, what they do is that they will drive all the liquid with them, yeah? So you can move your liquid, all your liquid, just by applying an electric field, yeah? And this is what we call an electroosmotic flow. Yeah? Is that clear? Yes.
Are the anions not flowing the other direction to the positive electron?
Yes, also, yeah.
They also create flow, right?
No, only the cations because they are closer to the surface. Yeah.
Okay.
And then you can quantify your electroosmotic flow with, which depends on the electric field you apply. So if your electric field is higher, then you have a higher mobility of your ions, and what is called the electrophoretic mobility, so the mu. Yeah. And what is important that this mu will depend on the surface properties. Yeah. So it will depend on the number of charges you have on the number of on your surface, and also the number of charges you have in your liquid. Yeah. And then the surface properties are characterized by what is called the zeta potential. Yeah. And so if you change the pH, for instance, if you change some properties of your surfaces, yeah, you will change. If you change the pH, then you will change the amount of charges you have on your surface, and then you will change the flow you can create because you change your zeta potential. Yeah. And what you see here, so if you change your pH, then you will change your electroosmotic mobility, and then the flow you can create in your channel. Yeah. So what is important here is that if you have, for instance, a glass surface which is not coated, and then the charge on the surface can vary, then your flow will vary. Yeah. And then if you can coat your surface, then you can control the amount of charges you have on your surface, and then you have a better control on your flow. Yeah. So if you do, if you work with electroosmotic flow and capillary electrophoresis separations, so the first rule of the coating is that you can control the amount of charges you have on the surface. Yeah? And then if you can control that, then you have a control on the electroosmotic flow, so the direction of the flow, but also the intensity of the flow. Yeah? And another role of the coating is that you will decrease the amount of interactions between your biomolecules and the walls, yeah? And then you have no adsorption of your molecules on the walls, yeah? That may change the charges, but if you want to separate the molecule, then you will have also some peak bordering, yeah? And then, so most of the time people are working with adsorption strategies, yeah? And they work with molecules which are charged or neutral that can interact with the wall and can coat the wall, yeah? But you can also do a covalent coating, but most of the time people prefer to work with adsorption of molecules on the surface, yeah? And I have 2 examples here to show you 2 different strategies. So in the first example, yeah, these are PDMS chips, but it could be also another material. And then the coating which is used here is to use different layers of polyelectrolytes. So polyelectrolytes are just like a large molecule with a charge, yeah? And then what they do is they alternate positively and negatively charged molecules. So PB is the cationic one, and DS is the anionic one, yeah? And what they look here is that they look at the effect of the pH on the electroosmotic flow, yeah? So if they start with a surface which is not coated, then they see that they have an effect of the pH on the electroosmotic flow, yeah? And after they add the first layer, yeah, and then they can see that they can reverse the electroosmotic flow because they change the charge on the surface, yeah? But they also have a bit of variation. And then after the second layer, they can better stabilize their electroosmotic flow in the channel, yeah? And then after they look also at the separation of biomolecules, yeah? So in the dashed line is the native surface, so if they don't apply any coating, yeah? So they separate 2 molecules, and what they see that if they don't do any coating of their surface, here the 2 peaks that will correspond to the 2 molecules are broad, yeah? So here you just have 2 molecules, so you don't care so much because you always have a nice separation, yeah? But if they have more molecules, then maybe these peaks can overlap, and then you cannot separate your molecules anymore, yeah? And this brown bordering is coming from the fact that the molecules will interact with the surface. So instead of having all the molecules coming out together, then they will spread, and then you have formation of a larger peak, yeah? And if they apply the strategy with this multi-layer coating, so with this PDDS, what they see is that they decrease the amount of interactions between their molecules and the surface, yeah? And you can observe that because they have very, very sharp peaks for their separation, yeah? So here the coating has 2 roles, yeah? They can control the direction and the stability of the electroosmotic flow, and they can also reduce the amount of interaction between the molecule they want to analyze and the walls, so they get a better separation. And another example here, so it's also adsorption, yeah? So another coating which is widely used is based on cellulose molecules. So you have different types of cellulose, but they are all polymers based on sugar units, yeah? And here, so they look at glass and plastic microchips, so it really shows that you can, that the coating is not specific for a specific substrate or material to make your chips, yeah? So they adsorb these different cellulose materials or other actually. This is this is an acid here, and this is a PEG, polyethylene glycol, yeah? So here, if they have almost no coating here, what they see is that they cannot have a good separation of their molecules, yeah? And then they try different coatings. So here they do a polyethylene glycol, and they start to separate a bit their molecules, but it ends up as a larger potato peak, so they don't really have a good separation, yeah? And after here they try different cellulose-based coating, and what they can see, they have a more stable line for the separation, and they can very nicely separate the different molecules they have in solution. Yeah? Is that clear? Yeah? And that brings me to my conclusion. Yeah? So what we were discussing at the beginning, and we started to discuss also yesterday, is that in microfluidic devices, but also in general miniaturized devices, yeah, surfaces are becoming more and more important, because of the fact that the surface to volume ratios varies with 1/r, so the smaller the distances, the more important the surfaces, yeah? And they should not be neglected, yeah? So they can have undesired and unexpected effects, so that can be positive, like some example we were discussing at the beginning of the course. For instance, if you want to carry out reactions that are catalyzed under acidic conditions, but it can also have negative effect that you have adsorption of your molecules and you lose your information on the walls of your devices. Yeah. Then we were discussing, giving basic definitions about surfaces. We discussed the different nature of surfaces you can find in microfluidic devices, so glass, silicone, and polymers, and also gold is used. Yeah. And then we discussed how you can modify surfaces. So there are two main general approaches. So adsorption, so physical interactions between your coating and your substrate, yeah, or a chemical and covalent approach where you really have like chemical bonds between your coating and your substrate, yeah. And then if you go for a covalent approach, then you need to have a protocol which you need to adapt your protocol depending on the nature of your surface, yeah. So if you work with glass and silicone, you will work with siliconization. If you work with gold, you will work with thiol molecules. And for polymers, you have to look at the chemical nature of the polymer, what you have on the surface. Yeah? And what is important is that you keep in mind what are the advantages or drawbacks of the two approaches. Yeah? So adsorption is very easy to implement. Yeah? So you just incubate your surface with what you want with polymers or proteins you want to immobilize on your substrate. So it's very easy, but it's not very stable. So you may have to check regularly that your coating is working properly. And then if you have a bit more time, or if you want to have something which is much more stable, then you can go for a covalent approach. But you know that it will be like more difficult to implement. Yeah. So this I've already said. Yeah. And then after we were discussing some applications where you will need to modify your surface properties. So for instance, if you want to control the hydrophilicity or hydrophobicity of your surfaces, if you want to immobilize biomolecules, yeah, this one I removed it because I will discuss it later. And then at the end, we discuss also the importance of the surface properties more to control your flow, if you work with electroosmotic flow, and if you want to separate molecules. So we only discuss the adsorption of the biomolecules on the surface. Do you have questions? No? Then, well, the lecture is over. Yep. So have a nice afternoon.